right, so good morning, everyone. Today we're going to continue talking about some hypothesis test procedures, and specifically we'll talk about a couple different tests we use to assess sample variances. And thanks for submitting your first assignment. I'm in the process of going through those. In general, those are in pretty good shape. I'll have a second assignment going up in the near term that'll cover the material for this week and part of next week. And then from a big picture standpoint, like I said, today we're talking about tested variances, and we'll talk about a 1 sample and a 2 sample variant. The next due date will be an introduction for your term paper, and so that'll be due this Friday. And so for the term paper, we're basically going to work through this iteratively over the course of the semester. And so, for example, the first deadline after the topic submission, which we had done previously, will be the introduction. And then we'll build off that with a subsequent submission that focuses on a literature review that will basically build off the introduction. And then beyond that, we'll start doing separate sections regarding our data, our analysis methods, preliminary results, so forth and so on, culminating in the final term paper at the end of the semester. And then the assignments moving forward will be roughly every other week. So the next due date there will be a week from Friday, February 19th. Okay. And so after today's class, you'll have 2 additional tests in your toolbox, essentially. The first of those is a chi-square test, and there are a variety of different applications for the chi-square test, and you've probably seen some of these in prior classes, but today we'll talk specifically about the case where we're assessing the variance of a single sample. And then we'll also talk about an F-test, which can be used to compare the variances between 2 independent samples, okay? Okay, and so from a big picture perspective, it's sometimes of interest to us to determine whether or not a sample variance is greater than, less than, or equal to some specific reference value of interest. Or more commonly, we'd be interested in determining if the variances between 2 samples are different from one another. And there's a variety of reasons why we'd be interested in that. In the first case, when we're concerned with just a single sample, we'll be working with a chi-squared test of variance. And in the latter case, there are a wide range of different tests that can be utilized. The one we'll talk about today is the F-test. I should note the F-test is simple as compared to these other 3 tests that are listed here, Levene's, Bartlett's, and the Brown-Forsyth test. But the advantage is it's simple, straightforward to apply, and this would be a nice simple test we could do if we're trying to determine whether or not, for example, to use Student's or Welch's t-test in order to compare sample means, because I know that question had come up last week. And if any of you are using any statistical analysis software programs, so SPSS, for example, if you run an independent sample t-test, it will run both Student's and Welch's, and it will also run Levene's test, which we're going to put off until a little bit later in the semester because we need to cover some prerequisite material before we get into that. But these are all different variants that are all aimed at just comparing the variances between 2 samples to determine whether or not they're significantly different from one another. And the reason why that's important is that a lot of the methods that we'll talk about this semester will make some underlying assumptions about how the data are distributed. And one of those common assumptions are that the variances are equal across the samples that we're comparing. So just to give everybody a little bit of context there. And so first of all, chi-square distribution, let's just see, I guess, how much background knowledge we have here. So how many of you are familiar with the chi-square distribution in some form or fashion? You want to give me the thumbs up or raise your hand, just so I've got a sense of context here. So Jordan, if you don't mind, can you let me know how you're familiar with the chi-square test?
I'm pretty much just familiar with the name. I just know that it's kind of part of like a ANOVA process.
Okay. I was wondering, because oftentimes in transportation engineering, I think the first time you'd probably be introduced to that is when you're comparing whether two distributions are similar or different from one another. So I thought that might be where we went with that. But in any case, the chi-square test, as I had mentioned previously, has a lot of applications in probability and statistics. And so the case we're going to talk about today is going to focus on hypothesis testing. And next week, we'll start talking about confidence intervals. And those are basically analogous ways of looking at the same underlying research questions of interest. And so in this setting, we're basically interested in making inferences about the standard deviation of some population or the variance of that population. We'll use those standard deviation and variance terms interchangeably, of a normally distributed random variable. One quick caveat here, we'll also start talking a little bit over the coming weeks about how we assess whether or not data are in fact normally distributed, because that's another underlying assumption for several of the methods that we'll be talking about. And on Wednesday, we'll start talking a little bit about non-parametric tests, which basically forego that normality assumption, but just wanted to bring that point up. And so in addition to that setting we'll talk about today, there are a wide range of other applications where we use the chi-square distribution to compare how well a actual observed distribution of data fits as compared to a theoretical distribution. So we can use the chi-square to assess normality, for example, or to assess competing regression models on a given data set. And so we'll talk about all those different types of applications in the future. And so from a big picture standpoint, a chi-square distribution is going to be defined by its number of degrees of freedom. And this basically is a distribution of the sum of squares of some independent stand-up normal random variables. And so we'll talk about that a lot more when we get into the regression framework. But as we look at the shape of the chi-square distribution, you'll notice it's quite different, at least at low sample sizes, as compared to what we've seen previously with the normal distribution. So we tend to see that this distribution is skewed, and at low sample sizes, it's also generally truncated. So we'll have, at low degrees of freedom, a relatively large number of small values, and generally across the distribution, we'll also have a relatively large number of extreme values in the positive direction. So you'll see this positive skew. And eventually what happens with the chi-square distribution, and you can probably get a sense of this just from looking as we increase from 2 to 5 to 10 degrees of freedom, eventually this distribution starts to resemble a standard normal, and that largely relates back to the final bullet point here. That this is basically can be thought of a distribution if we sum a series of random variables, if we sum the squares of those variables, that distribution will eventually approach a normal distribution, just given the fact that we're summing other normally distributed random variables, okay? And so a few of the key features of the chi-square distribution that are of interest to us here. So first of all, as you can see here, it's generally asymmetric. And instead of ranging from plus or minus infinity, it has a minimum value of 0 and ranges towards infinity on the top end of the distribution. There are also different chi-square distributions for each degree of freedom, as we've talked about previously. Now, in the case of normal distributions or T distributions, in those cases, what we're generally changing is the location of the distribution and the shape of that distribution based on the variance. But in this case, basically that one chi-squared parameter is changing both the central location as well as the shape of that distribution. And so specifically, it may or may not be obvious as we look at this, but in a chi-squared distribution, the mean value of that distribution is equal to its degrees of freedom, interestingly. So with 2 degrees of freedom, the mean of this chi-square distribution is 2. Likewise, the mean of this chi-square distribution is 5 and 10, and so on. And so intuitively, I guess you might think that this would be centered right above that point, but keep in mind these distributions at least at the lower degrees of freedom, tend to exhibit significant positive skew. And as a consequence of that, it's not falling quite above the mean value there. But so the mean of this distribution, if we were to integrate this, would be equal to the corresponding degree of freedom. And then similarly and interestingly, the standard deviation of that chi-square distribution is going to be equal to twice its degrees of freedom. Okay, so just some general background. And so as we conduct these chi-square tests, these will be the distributions from which we'll be drawing those critical values. And so as you can notice here, this gives you a sense of how those critical values will tend to increase or decrease as we vary the degrees of freedom. Okay. And so in this case, the ratio of this, if we take a sample variance and compare it to the population variance from which it is drawn, that test statistic is going to follow a chi-square distribution, okay? So in this context, what we're basically going to do is use the chi-square test to evaluate the null hypothesis that the variance of some population of interest, so sigma squared, which is going to be estimated based on some sample data, we're going to assume that that's equal to some reference value of interest. And we'll talk about a specific example of that today, but that reference value could be based on existing data, or there could be a hypothetical or theoretical reason why we're interested in whether or not the variance is less than, greater than, or equal to that specific value. And as before, we'll have a series of competing alternate hypotheses, and we'll talk about how we determine critical values to compare the test statistic under any of these various hypotheses, okay? And so the actual test statistic is just shown as demonstrated here. So really simple and straightforward. All we're doing is taking n-1, so our sample size -1, and that corresponds to the degrees of freedom for the chi-square distribution we had shown on the preceding slide. And we're just taking the ratio of that sample variance to the population variance or reference value to which we're comparing. And so if the null is true, so hopefully this will all make sense to us here. If the null is true, what would be true of that ratio s squared over sigma squared? If the ratio s squared over sigma squared sub naught, if our null is true and those variances are equal to one another, then that quantity would just be equal to 1, and this chi-squared statistic would just be equal to n-1, which to the preceding point, n-1 is just telling us our degrees of freedom, or whatever the mean value is that corresponds to that chi-square distribution, okay? And so as a consequence then, if we think about this intuitively, as our sample variance gets relatively small or large as compared to that reference value to which we're comparing, then what's going to happen as a consequence is we're going to fall into the more extreme ranges of that chi-square distribution, which would give support in refute of that null hypothesis, and would suggest that there's a difference between those. And so again, if there's not a difference between those, then this simply converges to the corresponding degrees of freedom for the sample, which in this case would just be n-1, okay? So again, just the chi-squared test statistic is just the ratio of the sample variance over the population variance times the corresponding degrees of freedom for the test, okay? All right, and so after we've calculated that test statistic, again, we're going to go back to our reference table. In this case, this looks fairly similar in nature to what we saw in the case of the t-test. So just to refresh everybody's memory, in the case of the standard normal, in that case, we just have one fixed table because there's one known standard deviation of 1 and a known mean of 0 for that distribution. And so we have just the single reference table. In the case of the t-test and the chi-squared test, the shape of that distribution is going to vary based upon the degrees of freedom. And so as a consequence, we'll basically have one unique distribution that corresponds to each degree of freedom. And this is showing us what the critical values are for the lower and upper bounds when we're conducting these statistical tests, okay? And so, as I had noted previously, these aren't going to be symmetric relative to one another. And so, if we look at the bottom 5% here versus the top 5% of the distribution here, those aren't going to be symmetric about the median or the mean of that distribution. Although, as that sample gets larger, they're going to become closer to symmetric. As you'll notice down here, we're ranging from 43 to 60 to roughly 80 in that case. And those will continue to converge as that sample gets larger and larger. And as it approaches infinity, it will eventually converge towards normal. But in the case where we're working with relatively small samples, you will see relatively drastic differences between the lower critical region and the upper critical region. And that should be obvious just from looking at the shapes of these distributions. So if we take the bottom 5% from here, we would have a much smaller value than the top 5% of that corresponding distribution. Okay. And again, to use this tabular summary here to determine the critical values, all we need is our degrees of freedom, which we'll denote as K here. You'll also see that denoted as DF. That's just our sample size minus 1, again, just as it was in the case of, say, a one sample t-test. Okay. All right, and so we're going to work through a sample problem from a few different perspectives to demonstrate these tests of variance. And so if we look at the research data, it generally suggests that if we see higher variability in travel speeds at a given location, that crash risks tend to increase as a consequence of that. And that should make sense intuitively. If you've got a mix of vehicles and there's a lot of variability in terms of the speeds of those vehicles, you'll have faster vehicles approaching slower moving vehicles and trying to navigate around them, or you'd have risks of rear end collisions, for example. And so from our perspective in transportation, we'd like to minimize that variability to the extent possible. And so with that pretext, in this case, we're hypothesizing that the installation of a speed feedback sign may help to reduce speed variance at a given exit ramp. And so this actually parallels a study that's ongoing currently for the Michigan DOT that we're working on, where we've installed these signs on exit ramps where drivers have to rapidly reduce their speeds from 70 or 75 miles per hour to a significantly lower ramp entry speed. And so as a consequence of that, we do tend to see quite a bit of variability as drivers are navigating those ramps. And so let's say hypothetically, we have pre-existing data that tells us the variance in speeds at a given ramp where this device has been installed is roughly 15 miles per hour squared here. And based on that, we've collected a sample of speeds from 10 vehicles, and we want to use the chi-squared test to determine whether or not that sign installation has reduced the variance in the sample data from this field study as compared to that 15 mile per hour squared variance reference value we're comparing to, okay? And so we've got observations here that are sorted in ascending order. It doesn't necessarily imply that there's any specific order or need to do that. That's just the way that I've set the data up in this context here for everyone's reference. And so we're going to take this data and basically apply the chi-squared test. And so it was given to us that the reference value to which we're comparing is 15. We can use these data to calculate the sample mean. And so again, just summing these 10 observations, dividing by the sample size, gives us a mean of 32.0 miles per hour. Likewise, we can then use that quantity to estimate our sample variance. So taking each of these individual observations, subtracting off the mean of 32, squaring it, summing over the 10 observations, and then dividing by 10 minus 1, given the associated degree of freedom that we're losing there. And that gives us then a sample variance of 8.22. I've omitted the units here, but again, that's miles per hour squared. And so now the question is whether or not that 8.22 is significantly different from the 15 that we're comparing it against. And so we use the chi-squared test to conduct that assessment, okay? And so again, real simple and straightforward here. We're just taking the ratio of our sample variance of 8.22. We're dividing by 15 and we're multiplying by our corresponding degrees of freedom, which are 9 in this case. And so our calculated test statistic is going to be equal to 4.93. And so we're going to compare that against our chi-square distribution table and determine the critical value. And so if we think about this from a big picture perspective, and apologies, I didn't talk through this in great detail previously, we can conduct this as either a one-sided or a two-sided test. Now, in this case, we were specifically interested in evaluating whether speeds were reduced with the installation of these speed signs. And so with that being said, we would expect that our variance would be lower. And so which side of the distribution would we be interested in looking at here for our rejection region? Anybody? I'm fairly certain I stated that question correctly this time, so. Are we interested in the lower tail or the upper tail? Folarin.
I'm, I'm not really sure.
So if we think about the test statistic, Folarin, the way it's structured, we're comparing the sample variance based on our data to the reference value of interest. And so in this case, we're presuming that the speed feedback sign would reduce our sample variance relative to that reference value. And so we would be interested in rejecting the null if this quantity was small compared to this quantity, right?
Yeah.
And so with that being said, if this is fixed and if this is small relative to that quantity, where would we be interested in rejecting it? Small values or large values of chi-squared?
Small values.
Yeah, so in this case, we'd be interested in rejecting at smaller values. Okay, so the lower tail here is at 3.325. The upper tail is at 16.92. And in this specific case, we would be interested in that lower value. And so just to get the nomenclature here, so this is a chi-square distribution at significance level alpha, or that, now I should preface that. Corresponding to the upper alpha percent or proportion of that distribution. So I want to be careful not to misconstrue significance level here. But if we were concerned with the upper tail of that distribution, we'd be looking at sigma squared 0.05. In this case, we're concerned with the lower tail, so it would be chi-squared 0.95 with n minus 1 degrees of freedom. So we had a sample size of 10 here. We're reading across the line at 9 degrees of freedom. Okay. And so in this case, 3.325 is the value that we're interested in comparing against. And if our test statistic is less than that, we would reject the null. If it's greater than that, we would have insufficient evidence to reject. And so in this case, since we are above that lower critical value, we cannot reject the null. So even though our variance is decreased in this setting, it hasn't decreased to such a magnitude that we can conclude that that would be improbable at 95% confidence. Okay. So while our evidence suggests that the variance has gone down, we don't have sufficient evidence here to reject the null. Okay. Okay, so extending that, we can basically take that same approach we had just worked through and apply something similarly to compare the variance between two samples, as opposed to comparing one sample to a reference value of interest, okay? And so to that end, we've established previously that if we take the ratio of the sample variance to its population variance, that follows a chi-square distribution. And likewise, if we were to compare the ratio of one chi-square distributed variable to another chi-square distributed variable, in this case, comparing one sample variance to another, then that resulting ratio would follow the F distribution. Okay, and so a quick show of hands here as well. How many of you are familiar with the F distribution? Don't worry, I'm not going to call on you for this one, but it doesn't look like we've got a little bit of familiarity here. I would say probably the most common application you would see this, you might have saw it within the variance context we're going to talk about here, and then you'd also see it frequently in analysis of variance or ANOVA tests, and then we can also use it as just a general goodness of fit test for various types of regression models. So we'll be working with the F distribution quite a bit moving forward. Now the F distribution is also unique from any of the preceding distributions that we've talked about in this course. Because in this case, if we think about the example of taking two sample variances, each of those sample variances would have corresponding degrees of freedom. And so if we had two samples, we'd have degrees of freedom of n1 minus 1 and n2 minus 1 for those samples respectively. And so depending on those numerator and denominator degrees of freedom, both of those are going to play a role in terms of what the shape of this distribution looks like, okay? And so this is showing us one example F distribution. As I click to the next slide, we'll see a few additional examples here. And so as I had alluded to, the F distribution is somewhat unique in that its shape depends upon both the numerator and denominator degrees of freedom. And so as you see right here, this is just an example of an F distribution with 5 degrees of freedom for both of the samples versus one that has 5 degrees of freedom for the first sample and 15 for the second sample. And so the shape of this distribution is going to vary on that basis. And consequently, this makes it a little bit more challenging for us in trying to just simply determine what a critical value is to refer to, because we can't condense it all into just one nice simple table. And so we'd actually have a different table in this case. The way it's typically done is we would establish a table that corresponds to a specific significance level alpha. And for that level of alpha, we would provide a tabular summary of how the critical value changes based on the numerator degrees of freedom and the denominator degrees of freedom respectively, okay? This will probably make more sense as we start getting into the actual application here. But since these the shape of this distribution varies based upon the two samples, it's less straightforward in terms of determining what our appropriate critical value is. And so in our setting, what we're interested in doing is evaluating the null hypothesis that the variance of our first sample is equal to the variance of our second sample against any of those 3 competing alternate hypotheses. And this is probably about the simplest test statistic that we're going to work with in this course. So the F test is simply equal to the ratio of those sample variances, okay? So S1 squared over S2 squared, or alternately S2 squared over S1 squared. The manner in which we compare this ratio, so what sample goes in the numerator versus the denominator, is going to be entirely arbitrary in this case. We would just want to make sure that when we select our critical values, we're thinking about how these hypotheses are structured in comparison to the way that test statistic is structured, okay? And so as I had alluded to, the critical values in this case are going to be unique. And so we have different tables for each specific level of alpha. And so what we see right here is a table for alpha of 0.05. And in this case, the columns correspond to the degrees of freedom for the first sample, whereas the rows correspond to the degrees of freedom for the second sample. And then this also shows us as we converge towards infinity in either direction, how these values change relative to one another. Now, one quick point I should mention here, if we think about how this F test is structured, if we're having the first sample in the numerator and the second sample in the denominator, we would want to reject at relatively high values. And so just thinking about this conceptually, what that means is if you had a sample size of 2 in each of those groups, which is the smallest sample we could have in order to calculate a variance, that ratio would have to be greater than 18.51 in order to determine those are significantly different from one another, okay? And then as we begin increasing the degrees of freedom or increasing the sizes of those respective samples, you'll notice those ratios tend to decline relatively rapidly. And in the most extreme case, as we approach infinity, basically any difference greater than 1 In that case so for example, if we could observe the entire population, if our critical value, if our calculated test statistic was greater than 1, we could reject in that case. And then, the smaller the sample size is, the more evidence we would need in order to reject that null hypothesis. Okay. Now, it should also be noted here, and one thing you want to be careful of, these F tables are typically structured such that they're corresponding with just the top tail of that distribution. And so if we wanted to conduct a two-sided test, or if we were interested in what's happening on the lower end of that distribution, in order to determine that lower critical value, we can basically make use of the fact that these critical values are going to be symmetric from that perspective. And so, for example, if we had 5 degrees of freedom in both the numerator and the denominator, you'll notice our critical value here is 5.05 for the upper tail of that distribution. And so for the lower tail of that distribution, we would just have 1 divided by basically the inverse of that quantity. So 1 over 5.05, or roughly 0.19, 0.2. Okay. So hopefully that makes sense. Just keep that in mind as we're conducting these tests. And the other thing you'll want to note there then is, let's say hypothetically we're conducting a two-sided test at a significance level of 0.05. In that instance, we'd want to use the F table for alpha of equal to 0.025. Okay, so if we were to conduct a two-sided test with these critical values, our total probability of type 1 error in that case would be 0.1, because we're using the 0.05 table on both extremes of the distribution. So just keep that fact in mind as we work through this as well, okay? All right, so we're going to return to the same speed data that was presented previously. So the right column here should look very familiar to you. That is the exact same data summary that we had seen previously. And we're also providing some sample data that had been collected before that speed feedback sign had been installed. And so we're going to basically work through the exact same procedure we had demonstrated previously to calculate those F tests. So we first of all need to determine the sample variance for the period before installation of that speed feedback sign. And so the mean of this column is 35.8. It's sample variance, again, differencing each of these from 35.8, squaring that difference, summing, and then dividing by the degrees of freedom. We get a sample variance of 15.07. Again, omitting the units of miles per hour squared here. And so that's very close to the hypothesized value of 15.0 we had tested against previously. And our second sample, we'd already walked through these. The sample mean is 32 miles per hour, and the variance in this case is going to be the same, 8.22. And so we're going to take the ratio of those respective variances then and assess whether or not we saw a significant reduction in speed variance once that sign had been introduced. Okay. And so application, again, really straightforward here. We're just taking 15.07 divided by 8.22. And so our calculated F statistic is 1.83. And we're going to compare that against the corresponding critical value. And so in this instance, we need to think about this. So we'd want to reject the null if this ratio was particularly large. So we are concerned with the top 5%. So we'd read the number directly out of this table in this case. Our sample sizes are 10 and 10 in each case, so our corresponding degrees of freedom are 9. So we'd read down this column, and 9 we'd read across this row. And so that would basically give us a value F 0.05 with 9 numerator, 9 denominator degrees of freedom, or a critical value of 3.18, okay? And so if the ratio of our first variance was more than 3.18 times as large as the variance of our second sample, we could reject the null. In this specific case, we're less than that upper critical value. And so again, we failed to reject the null, and we don't have sufficient evidence to claim that there's a significant difference here in these respective sample sizes, okay? Now, interestingly, just from looking at this table, we could get a sense in terms of how large that sample would need to be in order for us to reject that null. And so we'd basically be scanning until we got into that 1.83 range. And so you'll notice it's going to be right down in these respective areas. So as our sample sizes approach roughly 30, we'd have sufficient evidence, and we'll talk in some subsequent lectures of how we can basically kind of back calculate to determine how large of a sample would be necessary for various types of experiments or other analyses of interest here, okay? Now we can, just to kind of demonstrate that looking at the other side of that distribution, we're going to return to the exact same example problem, except now we're just looking at the opposite ratio. So we're comparing the variance of the second sample to the variance of the first sample. And so since we don't have an F table for alpha or for the probability 0.95, we're going to work with the 0.05 table in this case. And so all we're doing here obviously is just the inverse of the relationship we had done previously. So we're taking 8.22 over 15.07. That F statistic is 0.55. And now when we want to determine the critical value, in this case, we would be rejecting the null when this value was relatively small or smaller than we would expect to see just by random chance. And so the critical value in this case, instead of 0.05, we're looking at the 0.95 value with 9 numerator and denominator degrees of freedom respectively. And so all we're going to do is we're just going to take 1 divided by that 3.18. And so if our F statistic was less than 0.31, we would have sufficient evidence to reject. In this case, we're not quite that low, just as we're not quite that high in the preceding example. And so in this case, we do not have sufficient evidence to reject the null. And so consequently, we can't claim that those variances are significantly different from one another. Okay. And so a quick follow-on question here, and Jordan, I hope you don't mind if I pick on you, but you had asked me this question last week, so we'll circle back and actually have you answer it. So let's say we wanted to compare the mean speeds between these samples. Should we use Student's test or Welch's test?
I guess we should use Student's test because we can't reject the null, which is that the means or the variances are similar, right?
Yeah, exactly. So in this case, we'd be fine to use Student's. Now, with that being said, there's absolutely no problem to use Welch's. Welch's, you'd basically just be making a more conservative conclusion in this case. But the net effect here is that you wouldn't see a very substantive difference between those respective results. And so consequently, you could be comfortable applying either of those. Okay, so that's one potential application of the F test beyond just comparing the variances as we had worked through here. Okay. And so I believe that gets us through all of the testing content I had talked about today. Okay, so for the forthcoming homework assignment, we will have some tests of variance included there, as well as some additional tests that will be introduced over the next couple of lectures. The other near-term deadline relates to our term paper. And so the first step in that term paper, having finalized our topics, in each case is to write the introduction section. So I guess first of all, for my reference, can I get a show of hands or thumbs as to how many of you have written a paper that's been submitted to either a journal or a conference or something of that nature? So basically a peer-reviewed article. Okay, and just to make sure everybody's with me, how many of you have not done so? So everybody else put their hands and thumbs down. And hopefully I see a different set. Okay. So the first step in establishing or writing this paper, and I guess it's somewhat arguable, but one of the first steps is to just provide an introduction. And that introduction in part is demonstrating that your topic of interest is worth investigating, for example, okay? And so as a starting point for our term paper, this week we're looking for you to draft just a brief introduction section And the primary purpose of this introduction is to provide readers with some context for your study. So first of all, what are you researching? Why is that topic worthy of investigation? What do we know about it? What don't we know about it? And from your perspective, what's your objective, or what are your hypotheses that you're aiming to evaluate as a part of that investigation? Okay. And so with that being said, when we think about term papers versus, say, research reports, in a research report, we could be looking at a significantly larger, 10, 15-page introduction here in a report versus a research paper. We're typically limiting the introduction section to one, typically maximum 2 pages in length. And with that, we're also assuming the audience has at least a general knowledge of the domain that we're working in. So in this case, transportation and transportation engineering. And so you want to be somewhat careful not to get too far in. You want to give any reader with that broad background sufficient knowledge, but you also want to get at least some level of depth there as well for the informed readers who would be going through your paper. Okay. And so to that end, the next slide just basically goes through kind of a big picture perspective of how you should structure that introduction. And so as an example, let's think about a potential paper topic we could be interested in. And we talked previously and looked at some sample data that corresponded to motorcycle helmet use. And so let's just assume that I'm writing a paper on motorcycle helmet use and the impacts of helmet laws. So the first thing you want to do in the introduction is just start with the very big picture. So why is this topic worthy of investigation? Okay. And so to that end, just some general background, hopefully highlighting pertinent statistics that illustrate why this problem is important and worthy of investigation. And so in the case of motorcycle helmet use laws, we could state, national fatality statistics, and, we could talk about the thousands of people that are killed every year in motorcycle crashes throughout the country. We could compare differences at a big picture in terms of what the helmet use rate is in those fatal crashes. And maybe we'd even have helmet use rates either from non-fatal crashes or just from random surveys of the motorcycling population. And regardless of which way we slice that, we could make a pretty compelling argument that when you wear your helmet, you're less likely to be fatally injured as a result of a crash, and ergo, helmet laws are an important area of investigation. Okay. And so from there, we provided broad context for the study. So we talked about the fatality statistics. And then in our case, we're specifically interested in helmet use. So we've demonstrated that generally speaking, if you're wearing helmets, your odds of being fatally injured are less. And we can talk a little bit about the ways that we can try to incentivize helmet use from a policy perspective. And so we could talk about universal helmet laws versus secondary helmet laws. And again, just to refresh everyone's memory, universal helmet laws just basically means that every rider and passenger needs to wear a helmet while on a motorcycle. Secondary laws, like we see in Michigan, would restrict that use so that it's only required among specific subsets of the population. In our case, it'd be younger riders or riders who don't have sufficient levels of motorcycle training and rider insurance. And we could also, at a high level here, maybe provide a general comparisons of maybe some prior research that has occurred in this area. So there have been several studies that have examined motorcycle helmet use, and we can talk about sort of what those studies have shown from a big picture perspective. And then maybe, some we'd want to frame it in terms of why this would be worthy of further investigation. And so if we look at the Michigan case study as an example, the decision was made back in 2011-ish to weaken the helmet law. And as a consequence of that, maybe we'd be interested in writing a paper that examines what the implications of that decision have been. while controlling for the other factors that may warrant that type of investigation. Okay. Now here in the introduction, you can provide a just a brief overview, a Cliff Notes version of the prior research in this area. So you could note that, several studies have investigated the same issue, maybe in slightly different contexts, and the general findings of these studies are. We typically don't delve too far into the details in the introduction section here, so we're not necessarily talking about the methods that were employed in those studies. We're not talking about very specific nuances like the sample size, how the data were collected and analyzed, and so forth and so on. It's just largely big picture, culminating in formally stating what our research hypotheses are. And so let's say, for example, in this case, maybe we're just looking to determine what the impacts of that helmet law change are on traffic fatalities or societal costs resulting from motorcycle crashes. And then you can conclude by basically just a short description of what's coming in the subsequent sections of the paper. Now, in our case, since we're just starting the paper, we can probably omit that section until we have the rest of the paper written there, but that's just common practice oftentimes when we're preparing research papers. Okay. And so from my perspective, hopefully that gives you enough information that you're able to get started on this. I think one thing you could easily do is just take a few sample articles and just read through how those are written, and that will give you kind of a good sense of what we're looking for here. I think in most of your cases, you have topics that are relatively straightforward, and it should be fairly easy and straightforward for you to put together this introduction section. With that being said, if you have questions or if you want me to just take a quick look at what you're preparing, I'm happy to do so. And I should also note for the term paper, these are largely intended to be just kind of check-ins. So I'll go through and give you high-level feedback on the direction you're going with the paper. I'll also, depending how many other deadlines I have that week, I get very detailed with editorial comments and technical writing and things of that nature. And so I'll try to give you some constructive feedback from that standpoint as well. But that's basically what we're looking to get turned in for the end of this week. Okay, so I don't know if we have any questions on the term paper piece from anybody. Going once, twice, 3 times. Okay. And so the plan then moving forward, as I mentioned, that term paper intro is due by midnight this Friday. Assignment 2 should be up probably by the end of the day on Wednesday, depending on our pacing. But on Wednesday, we'll start talking about some non-parametric tests. And so that's basically tests we would apply when some of our underlying assumptions about whether or not data are normally distributed, for example, are met or not. And if they're not met, sometimes the t-tests that we've talked about up to this point aren't going to be the best choice for us from an analytical perspective. And so we'll talk about those tests on Wednesday. And then, that assignment will be out, and that'll be due a week from Friday. So with that, we will wrap a little bit early today. And if you have any questions, I can hang around after the fact here. Otherwise, I will see you all on Wednesday. Thank you.